Hi everybody, welcome to my technology channel. For a short time we organized with Peter so-called technology challenges to each other, where I already participated in a first episode on Peter's channel. Take a look on our discussion and the quiz he prepared for me. It was challenging, but I hope I did not so bad. Today it's my turn to invite Peter and talk with him about powder metallurgy. We will find out today how well Peter knows the technology. He is actually a great expert there, but some simple questions sometimes might be challenging. And in the end, I have a very special process for him, which is related to powder metallurgy, and let's see and find out how he has managed to answer those questions. Join us in these discussions, comment, and we meet again in 2 weeks on a Peter's channel, where we will again see me being challenged by Peter with another technology.
Hello, Peter. How are you today?
Hi, Akari. I'm fine, and I've really been looking forward to this today.
That's very cool because I also enjoyed our quiz last time, and as we aligned, this is my time to challenge you. And
Yeah,
I have prepared,
it's
sorry,
your revenge.
it's not a revenge. I have
Ah,
prepared something simple for you, but I hope you will still enjoy it. So I slightly changed the format.
yeah,
So it will be a little bit more interactive, and I hope the listeners will be also taking with us on the journey between technologies. Peter,
yes,
you are a metallurgist.
I am.
So you also have a Tech part of your channel name, as I can see here. So it
Yeah,
means you are not only metallurgist, you are an expert in powder metallurgy.
yes, that's my background.
And you know, that's funny thing is that my background also is in a powder metallurgy.
Mm.
So my studies initially were exactly of making carbides, powders, and various other powder combinations for coatings like and processes like PT and laser cladding.
Hmm.
So my roots are more or less similar to your roots,
Yeah,
even if I'm probably more on the ceramic and carboceramic side of powder metallurgy.
hmm,
That's why if I look on today's quiz, and that's where I want you to tell me what is powder metallurgy?
yes, yeah. That's a good one. Powder metallurgy started, in fact, many years ago. Uh, it was the only way you could make products in alloys that had so high temperature that you could not melt it.
Mm-hmm.
So a class example is materials made in tungsten. You're not able to melt tungsten products, so therefore you have to produce it powder metallurgically and sinter it. Um, so in basic, it's I often use the picture of a bakery, because in a bakery you have the flour. In a powder metal plant you have the metal flour. By that you can make different kind of breads, and you can also make different kind of metal components. So if you one day want to make stainless steel, you can do that. You can make traditional carbon steel. You can make what is that called? Uh, Different alloys, copper, aluminum, and some of these very special high temperature materials are very common, as well as electrical steel.
Yeah.
And some of the funny things, magnets, they are always made with powder metallurgy roots.
Yes, because you improve magnetic properties of materials by that. You know, when I
Yes.
was preparing this extra for you, and honestly, also trying to answer the question, what is powder metallurgy? I have not found anything which was more simple than a Wikipedia message, which seems it's a covering wide range of ways in which materials or components are made from metal powders. So it's very simple.
Yeah, very simple. Yeah.
If not too deep dive. So
Mm,
also a picture from internet showing that we have a powder, and then you
mm,
have various components like gears and so on,
yeah.
which you
Mm,
can produce using this technology, not if too
yes.
deep dive. So
Yeah.
let's
And
move forward. And I want to come back to your probably very young and times. can you name me the 4 main classical steps of every powder metallurgy process? Like not going to powder injection molding, not going to additive manufacturing. What were the real classical first 4 steps?
The manufacturing of the powder
Yes,
must be number one. So,
correct.
so typically the powder is made, you melt it and you atomize it. So that's the main way of making the powder. So it can be water atomized or it can be gas atomized primarily. There are also some advanced methods, but let's keep them out. Then next step is blending the powder or mixing it. It could be mixed with a binder system, or it could be mixed with a lubricant, or you can also make what you call blended elements. So take pure iron and add graphite, and when you sinter that, you have a carbon steel. So the next after mixing, it's pressing. So the compaction, it's a uniaxial compaction where you put the powder in a die and you have punches from top and bottom compacting it, and it can be more or less complex. It can be several levels of the punches. So today there are a pretty large degree of freedom compared to just 20 years ago. Then the final is the sintering process. And sintering is 3 things. First, you preheat to remove the lubricant, because you want to be able to control your carbon content, and the lubricant is a hydrocarbon. So you remove the lubricant in a preheating zone, then you go to the sintering zone where chemically it goes together. The powder particles, they don't melt typically, but it's like when you have snow in wintertime, you are in fact able to make a snowball by sintering it with your hands. Even though that is not melted, you can still compact it.
It's
So that
very
is
good.
sintering.
It's very good example. Peter, I must say, applause. You're really an expert in powder metallurgy. You exactly mentioned all 4 main steps which are classical powder metallurgy. From powder preparation, not going in details on methods, primary atomization. Then you have mixing and blending. You even describe the difference between mixing and blending, which is great, and compacting, and of course sintering.
Yes.
And now we move to next question. Can you name a typical products made by this type of processes?
Yes. What should I take? In automotive industry, in the motors of a car, there are a lot of components. The camshaft, some of the parts for the camshafts are made in powder metallurgy, and they were some of the first, the old parts that were started making. But the small teeth you showed on your first picture, that's also a standard. So for a clockwork in Switzerland, I am sure they use a lot of those in the watches.
They do.
Yeah. Because typically a product has to be a little complex because it is not like when you machine, you remove material, here you build it up. So the more complex, the less waste you have. So it's typically an advantage to go powder metallurgy if we have complex shapes and where it will be difficult to machine or costly to machine it.
Yeah, it's very good summary. I was surprised when I was searching about numbers, and still 80% of components made by powder metallurgy go to automotive. Like an example, transmission system of Ford. Yeah, very beautiful part. I tried to put for our viewers a couple of not everyday examples, like orthodontic brackets. People hardly believe, but they're also done by powder metallurgy.
Yeah,
and
they are.
some
It's a MIM part.
yeah. Anyway, it's still powder metallurgy. And then at the end of the day, what I found very interesting is the most expensive knives, kitchen knives, they're made from high-speed steels, made of powder metallurgy, because they get the highest hardness and actually extreme long lasting times, maintaining sharp edges.
And some of these knives are even made as Damascus design. So you when this is hipped, so hot isostatic pressed. So you take powder into a big steel can, and you put that into a hot isostatic press where it's heated to above 1,000 degrees and pressed with 1,000 bars. And if you in your design take two different alloys and you position them like that in the powder shape, and you press it, then you have the look of a Damascus steel. So it's cheating Damascus, but it's
cheating.
It looks pretty nice.
It looks very nice and has nice properties. I agree.
Yeah.
So let's move.
I tried to make a copy of it myself.
And successfully?
Yes, I have it in my garage.
Okay, I'm excited to see probably next time you make a video to show your own creations. So some fascinating facts. I choose also 3 fascinating facts, like a challenge to you as an expert. So tell me, powder metallurgy is quite commonly considered as a green process. What would you name an efficiency % of powder metallurgy?
I agree on the green. And it is mainly because of a high efficiency. Because the powder usage is typically above 97%. There are some waste in running in, and there could be some scrap once in a while, but I would say typical efficiency is 97%.
Peter, I love and hate you at the same time, because you exactly hit the number. Yeah, so it's very clean. And also what people quite often forget, you almost don't need any post-machining. So your machine removal rate is extremely low.
Yes.
Yeah,
maybe I wrote that number.
I have a reference for this. Maybe somebody was listening to you. So another one, can be compact considered as a final product? In a classical powder metallurgy. So you told us there are 4 steps: atomization, mixing and blending. Then you make a compact by pressing, and optically it might look very beautiful, like a real part. But can it be considered as a final product?
No, we call it a green part.
Yeah.
And the strength of that is typically below 10 megapascal. It's just strong enough to move it from the press to the furnace, but you can easily squeeze it with your hands.
That's a very nice answer. So it might look like a final product, but it's actually not dense. And I like this picture, which shows you an example between a raw powder formed product. So you basically densify it, but at the end of the day, you need a sintering process to get a final dense quality product.
Yeah.
And then we come to sintering.
Yeah, you can say furthermore, it typically doesn't have the right size, because during sintering, it also shrinks.
Correct.
So a typical shrinkage rate is 2 to 4%. So therefore, we make it typically in oversize.
Yeah, I remember calculations on my master classes for powder metallurgy. Find out the shrinkage rate of titanium carbides and some kind of binder. Oh, crazy stuff.
And Akadi, do you think the shrinkage is linear?
No.
It is not. we had a project some years ago with Trento University where we tried to design algorithms to foresee shrinkage as function of geometry, but we couldn't develop or define one algorithm. There were several algorithms depending on wall thickness or material composition or height or difference in wall thicknesses.
And even the sintering cycles.
Yep. Yeah, it's pretty difficult. So therefore, typically in metal powder factories, some of the important guys are the old guys who has been making the drawing for the tools for more than 20 years. They are the real experts because they have the experience and they're not able to tell you why.
That's when you really become an expert. I just feel it, yeah,
exactly.
smell it. Well, anyways, we are now entering the era where we always need to describe everything with a model, because otherwise you cannot automate it. So probably there will be more attempts using artificial intelligence to put that in the models. Let's see where it's going to bring. Peter, final question to this introductive quiz is, does sintering melt the powder metal?
No, typically not. But for some alloys you do. So I know you are in the hard metal world. And if you have a hard metal as a tool and you want to be able to work with it, you cannot use it if there are pores in it, because then it will be too fragile and it will break. So therefore, you typically sinter in semi-liquid state. So you have up to 20% liquid phase in the beginning of the sintering. Then shrinkage rate is a lot higher. You can have shrinkage rate up to 20%.
That's correct.
So it's pretty difficult to define it, the final shape. But by doing that, you can totally remove the porosities you typically have in standard sintering.
That's true. That's also, but also there you quite commonly move now to hot static pressing nowadays. However, the question you answered, you made an example with a snowball. Like in powder metallurgy, probably what's the most important to say is that the sintering process is kind of art of heat treatment. So we heat up below the melting temperature. We keep that to a certain extent and time, because you need time to get the processes happen, and then you get the beneficial dense properties. So it's like an ice cube inside of cold water glass. It's melting, but it's not really melting.
Yes.
And this is a fun fact which I liked. Peter, this now brings me to a quiz technology. So we introduced to people that's the powder metallurgy. And now I will explain you something which I would like you to find out what I'm talking about. Maybe it will be easy for you, but at the end of the day, powder metallurgy, as you mentioned, also used for combination of various raw powder materials, which you can bring together and get some benefits of that. In certain processes, you might use ceramic or hard metal or steel balls during the blending or mixing stage.
Yes.
So, because during this, when you rotate, the balls undergo mechanical impacts to the powder particles. They deform them, they fracture them, but they also cause welding, which is an important phenomenon of this process we talk about. So now I go to something which my early age was of where I first ever took this process seriously. As a young, ambitious person, I started to work on titanium carbide because it has lower density compared to tungsten carbide. It's easy to get, but titanium carbide is also not the cheapest material on the market. Nowadays, we talk about also laser cladding, brake disc applications. Titanium carbide is almost a standard choice by the companies to do it. When I was young, 15, 20 years ago, as a young student, it was not the case. And we were looking on titanium dioxide because it's extremely cheap and widely available material. So, and then we tried a method which you will tell me probably later, sooner or less, where we mix titanium dioxide with carbon powders in precise proportions. We bring it to kind of tumbler, and with the balls, we use titanium balls because they would remove you a certain amount of contaminations, because titanium carbide balls actually build your titanium carbide, even if they contaminate and wear. Then we perform this high energy ball milling process, causing reactions over certain time and these energetic cycles, which theoretically should lead to formation of titanium carbide out of titanium dioxide. Very nice and simple described on these images. What was the motivation behind? I told you already in a couple of words. So it's widely available, titanium dioxide. You could have an USP because you would be the first one to do something in other ways than people do. It's also environmentally friendly. And you can get, most important, customized microstructures. So you can variously play with titanium carbide grades and grains and particle sizes and properties. You could add some alloying elements and get really interesting results out of that. Of course, since that time, technology have moved forward and you have different and various way how you produce it. But that time it was interesting. What challenges we faced was that when titanium dioxide reaction with carbon takes place, it requires a high energy level.
Yes, absolutely.
And intense milling. To form this cycle and realize that you can get all titanium dioxide transferred to titanium carbide was not easy. So you, of course, can get some contaminations, because wear happens not only on balls, it can happen also on the housing of rotation tumbler. So you still can get some particles which you would not wish to have there because of aggressive milling. But the main obstacle was that time, and actually unfortunately probably remains for this method, is industrial scale up. So if somebody comes and says, I need 100 kg of titanium carbide, probably this would be a very nice method. But if somebody says, okay, we have a application where we need 100 tons of powder produced this way, this technology unfortunately failed to have it industrialization. And that's why it's not really widely used for high volume powder productions. So, Peter, we step to a question. What am I talking about?
The product or the process?
The process, technology behind.
It is called ball milling?
No, it uses ball milling, but there's a clear scientific name of this technology. Maybe you know it.
Some reactions going on in it that you typically don't see in ball milling. So there's some thermodynamics to it. And I could imagine that thermodynamic is a part of the name.
Correct. No, not directly, but...
Okay. Yeah. I don't know the process. I know the ball milling. I know how it works. I was a little in doubt when you told that you could just put in the energy to reduce the titanium oxide with carbon at room temperature.
I might doubt temperature. Of course, mechanical loading causing a temperature increase, but you need certain long cycles here to do it happen. And actually, due to energy, transformation take place. I can sign it that we got titanium. I personally did it in the lab. On a lab scale, it has functioned.
How high is the yield? Are you able to transfer all the oxides to carbides?
Honestly saying, I did it on a lab scale for maximum 2 kg of material. And it worked.
Okay.
Don't ask
for how
me
many
if it
hours
worked
did you ball mill?
Long time. Couple of days.
Very many hours.
Long days.
Several days?
Several days,
Yeah.
So it was not really efficient.
Upscaling is difficult.
Voila, you need a lot of energy to transform everything, because you test and then there is still titanium dioxide and then you move. So unfortunately for me that time, it was not a solution. I found another way how I got to my titanium carbide. Maybe I will tell you in one of other quizzes we do, because it's also related to powder metallurgy, because I was able to get it in a much higher quantities also. But you also had other problems with contaminations there. So anyway, Peter, the process is called mechanical alloying. So it's a solid state powder processing technology, which helps you to produce alloy and composite materials which are not achievable in conventional methods in casting. So the core of there is that you have a repeated deformation which causes you fracturing of powder particles and causes you cold welding process of those powder particles by the high energy ball milling. So you rotate it extremely fast and the balls fall down, causing you fracturing, which actually nowadays still quite widely used in nanostructured and nano-reinforced materials. So basically you alloy powders not during sintering stage, you alloy them by cold welding. And that's
so
how
you
your
make
transformation.
you typically call it.
Yeah, so that's how you also transform titanium dioxide to titanium carbide with this permanent fracturing and causing carbon to react with titanium. So, and as I said, which is, in my opinion, the biggest problem of this technology is the scalability.
Yeah, and it's costly.
It is costly.
Yeah.
Okay,
I'm
Peter?
typically on that side of it because I'm the guy purchasing the powders.
That's true. So, however, for some prototyping, and because I know the latest studies all go on these high entropy alloys, something which you not can get in conventional methods by blending powders and so on. There, it's still quite commonly used, at least what I see in papers and where the discussion about mechanical alloying goes. Maybe some who listen are experts in mechanical alloys and alloying and can share their comments and their perspective on this technology. For me, unfortunately, it's something which remained on a scientific level. I know it was developed in 1960s in US in a laboratory, and it actually was hidden in a laboratory because it's the only way for them to get some kind of oxide ceramics. And then it went more public. It was one moment very popular, especially for something which you would not get in a, let's say, a conventional way for so small volumes, extremely expensive and high-end applications, even in space. That might be still a technology to use. High scalability, for example, for automotive market, nah, I don't see it there. But I hope you learned something and I could surprise you with something on a powder metallurgy side.
Yeah, that was great. I learned something new about mechanical alloying now.
Okay. Thank you, Peter, for your time. And now it's your time to challenge me.
Yeah, thank you.
I hope you have enjoyed this series. And if you like it, please subscribe to our channels, to Mai's and Peter's. If we get 1,000 followers on each channel, we will be able to do those quizzes live, which we're really curious and looking forward. We hope you will be part of these participations. If you want to challenge Peter with me, feel free to send me your technology examples and I will ensure we will get Peter's opinion on that. If you want to challenge me, please send your questions to Peter and let's see where we get. Thank you for your attention. Bye until next time.